Welcome. Today let's talk about the well-separated pair decomposition. So the well-separated pair decomposition is a great tool for designing geometric approximation algorithms, and our motivation for it today will be geometric spanners. So let's look at geometric spanners by example. So there's a game in the ruler of the plane framework. So in the connect game, there's a T-spanner game, and essentially we want to connect the cities such that between any pair of cities there is a path that doesn't make a too large detour. So here we need this road to have a short detour, and we remove the last one to have a fairly compact network. So here I'm constructing such a spanner. So once more, a graph such that between any pair of points there is a path that doesn't make a too large detour. And again, so this edge, for instance, I'm not going to add because I also want the graph to be fairly sparse. So what I do in this example, I actually always take the look at the next shortest pair, see whether it is necessary to add an edge, and if it is, I do so. So here I'm trying a few which are no longer necessary because there is already a short path, but this one I need, and this one I also need, otherwise I have to do a large detour. And this is the next step. Okay, so that's geometric spanners. Let's have a closer look at this motivation. So here the problem that we were considering, we have a set of cities, we want to build a new street network, and we want to make this network not too large. And large in the example that we just saw was in terms of road length. Often enough we do it in terms of number of roads. So here, if I want to connect the cities, I mean the simplest graph to connect the cities is or at least the smallest, would be the Euclidean minimum spanning tree. So if I now want to have a short detour between any pair of points, then what we see here is that we have a problem. Namely, these two here, these two cities are fairly close, but if I want to travel between them in the network, I will have to go like this. So there are points that are fairly close but have a large distance in the graph. So the Euclidean minimum spanning tree is not a good choice for a spanner. Now, of course, you can say, I know the perfect spanner, namely the complete graph. So here indeed, between any pair of points, I have a very short path. I mean, I don't do any detour, but the problem, of course, is that I use a lot of edges. So what we would like to have, so a complete graph has, if I have n cities, I have order n squared edges, and what we would like to have is more something like a linear number of edges. And that's the idea of sparse T-spanner. So what is a sparse T-spanner? So sparse simply stands for the fact that it should have a linear number of edges. So a graph is sparse if we have a linear number of edges. The T here stands for how much detour we allow us. So the graph that you see here, that would be a T-spanner for instance, T is, let's say, 2. Because for any pair of points that I might be looking at here, let's say this one and that one, there is a path, and this is less than twice this length between the two nodes. Even the one down here, or the 2 points down here, so this is a path, this is less than 2 times as long. So this would be a T-spanner for T is 2. Probably also a T-spanner for some T smaller than 2. Okay, where do spanners occur? One application is when we want to build a network which allows fast routing. A typical setting is ad hoc or sensor networks. So imagine you have these smart sensors. You want to have a network so that you can move data or communicate fast within the network. Then you will want to build some kind of topology, and a spanner might be a good choice. Spanners are also simply a good tool for geometric algorithms design if you are in a setting where you need to represent all pairs of the distances between all pairs of points. Because a geometric spanner gives you a compact representation of all of those distances. I mean, if you need all these distances, but you have a sparse T-spanner, then you have a linear sized representation in which you can then hopefully quickly find out what the distance is that you're interested in. Okay, now let's formally define what we mean by a T-spanner. And we're looking at the geometric setting. So what we have is a set of points P in the Euclidean plane, or more generally in Euclidean space, or possibly in d-dimensional Euclidean space. And a T-spanner will approximate the following graph, the complete Euclidean graph. So what is the Euclidean graph? As vertices, I have my points. Then I have an edge between any pair of points. And the important part now is that the weight of that edge is simply the distance between those 2 points. So here I have u and v, and the weight of this edge is simply the Euclidean length of that edge. And on this complete Euclidean graph, we would now like to build a spanner of linear size. Yeah, so that's a goal. We have this complete graph, so the graph in black here, of course also including the red edges, and we would like to have a sparse graph, meaning a linear sized graph, linear in terms of edges, such that the shortest path approximates the weight in the complete graph. And the red graph here, depending on what how well you want to approximate, would be an example for that. And how well we want to approximate, that we express with this t. So we say that a weighted graph G on that vertex set is a T-spanner if it has a stretch factor or a dilation of at most t. So t is a value larger or equal to 1, and the graph has dilation t, or has a stretch factor of t, if for any pair of points the distance in the graph is bounded by t times the Euclidean distance. And the graph distance should approximate the distances also in the way that the Euclidean distance is smaller or equal to the graph distance, which you automatically get if, as edge weights, you take the distances between the points. And once more here, delta G in this case refers to the shortest length of the shortest path from X to Y in G. So that is a T-spanner. So for every pair of points, the distance in the graph should be at most t times the Euclidean distance. Here's a small quiz. You see this graph, and that what is the smallest t for which this graph is a T-spanner? And your options are square root of 2, 2, and square root of 2 plus 1. And the correct answer here is square root of 2 plus 1. Why is that the case? So let's have a look. So we have, let's see, we have this pair of points. Let's say this distance is 1. Then this distance is also 1. Of course, we have a square here. And this distance is square root of 2, because this is a diagonal in the square. So the graph distance, and this is also, so this path is the shortest path from here to there. The length of that path would be 1 plus square root of 2. Compared to the Euclidean length, this is 1 plus square root of 2. And in this graph, this is also the worst case. So for instance, if you take this pair here, then I can go here and here, and that actually gives you a detour of, so if this length is 1, modulo we scale. If this is 1, then this is 1 divided by square root of 2 and 1 divided by square root of 2. So that's 2 times square root of 2. So for this one, this detour is square root of 2. But we're interested in the worst case, and that's 1 plus square root of 2. So that is what a T-spanner is, but how can we compute T-spanners? I would recommend pausing the video and just for yourself think about, okay, what are good ways to compute T-spanners? Let me show you some common ideas, and for each of these ideas there are many different concrete T-spanner constructions. So the first one, which we already saw when doing the game, was a greedy spanner. So the idea of a greedy construction is the following. I add edges, or I look at pairs of points sorted by distance, because the closest pair of points seems to make sense to definitely add an edge there, although it might not be necessary. And then I take the next pair in terms of distance, so this is maybe the next closest pair. And I look at, is there already a path that is short enough? I mean, these were not connected, so there wasn't. And then the next pair might be, I guess this one maybe. And then the next pair might be this one here. But here, and this of course depends on my T, here I already see that there is a path which might be short enough. And if it's short enough, I'm not going to add that edge, and so on. So that's the idea of the greedy spanner construction. It is fairly expensive in terms of storage, because if I want to pre-compute all of those distances and sort them, so I'm pre-computing all distances between pairs of points and sort them, then I already need quadratic space. And then also every time I ask myself, should I be adding this edge? The way I can check that is to compute the current shortest path between here and there. But that again is an expensive computation. So this is a very nice spanner. It actually has very good properties, but it is fairly expensive to compute. Next class of spanners are cone-based spanners. So here the idea is that if I want to go from A to B, and there's at least some edge that goes more or less in that direction, then I can follow that edge, and from there again find an edge more or less in that direction. And to be able to do that, for every point, so let's say I take this point, I subdivide the space into a number of cones, and the more cones, the lower my T will be, and for every cone I connect to the closest. So I would do this edge, and now you need to tell me which one is closer. Let me just guess. This one. And I now do this for every point. So let's say this point here. I take a cone like this. In every set of cones like this, in every cone I connect to the closest, and so on. So those are cone-based spanners. And the last class I want to talk about are spanners that use distance approximation. So the idea here is, let's say these 2 points seen from back here are fairly close to each other. So the distance between these 2 points relative to the distance between that point up there and those points, so the distance between those two is fairly small, so I will definitely only need one edge from up here to one of those, and so on. And that's the idea of distance approximation, and that's the idea of a well-separated pair decomposition. So let's have a closer look at that next. So what is a well-separated pair decomposition? Let's start by defining what a well-separated pair is. So we have 2 point sets, A and B, and we call them well separated. Essentially, if the distance between A and B is large relative to the distances in A and relative to the distances in B. How do we formalize this? we say that A and B are as well separated if I can cover A by a disk and B by a disk, and I want to have disks of the same size and they have a radius r, let's say, and I can place these disks such that the distance between the disks is at least s times r. So then these 2 point sets are said to be as well separated. And you can imagine if I want to, if my input is 1 point set, then the idea of a well-separated pair decomposition is to cover all distances that occur by well-separated pairs. So for instance, in A, there are, A is a point set as such, and then some of the distances of the points in A I can cover by this well-separated pair A prime, B prime here. So again, I can cover these 2 point sets A prime, B prime, each by a disk of a certain radius, r prime, and the distance between these 2 disks is more than s times r prime. So that's a well-separated pair. Let's first make some observations here. So one, being s well separated is a monotone property in the sense that if I have a smaller s prime, so if a pair is s well separated and I have an s prime smaller than s, then the pair is also s prime well separated. Also, if A and B are both just for a single point, then so 2 points are always s well separated because I can take arbitrary small disks. Okay, so that's a well separated pair. What is a well separated pair decomposition? For this, first we need a definition, namely a definition for essentially saying all pairs of points. So this notation here, A cross B, denotes all pairs of points with 1 point in A and 1 point in B, excluding points that are both in A and B. So what do we want to have now? We want to have a small data structure that approximates all pairwise distances in a point set. And the data structure that should do this for us is the S well-separated pair decomposition. So the S well-separated pair decomposition covers essentially all pairs by a small set of S well-separated pairs. So what we want to have is we want to have a set of pairs such that, all the AI and BI should be, of course, points in subsets of P. If I have an AI and a BI, so a specific pair, then there should be no point that is in AI and BI, otherwise it would be also difficult to well separate them. I want to have that the union of my pairs should cover all pairs of points. Yeah, so for any pair of points in P, there should be a pair where this pair of points occurs. And all of these pairs should be as well separated. Let's see an example. So here I have a point set 1, 2, 3, 4, 5, 6, 7, 8 points. So I have 28 pairs of points. So I want to approximate 28 distances. And now for a suitable S, this is S well-separated pair decomposition. So let me briefly show what I depicted here. So for instance, I put those 2 points in a pair in A. Let's call this A1. Those 3 points in B1, and this is S well separated for suitable S. Likewise, this could be also B2, and it's well separated from A2. In here, these are difficult to separate, so I need to have, let's say, just a singleton A3 and a singleton B3, a singleton A4, a singleton B4, and so on. And in that way I get this list of pairs, A1, B1, A2, B2, and so on. And for any edge here, so let me pick any pair here, there's also a pair in my well-separated pair decomposition. So for this example, those two are actually covered by A1, B1. Okay, now we define what a S well-separated pair decomposition is. The first question is, does there always exist one? And of course, there is always one, namely the complete graph gives us a S well-separated pair decomposition. But that's of course not what we wanted to have. We wanted to have fewer than a quadratic number of edges. So we want to have a small S well-separated pair decomposition. Small, so when we talk about size, what we mean, so what do we mean by size? Size means the number of pairs. So I have A1, B1, A2, B2, and so on, and the number of pairs that I need, that I call the size of the S well-separated pair decomposition. And what we would like to have is linear size. And this linear factor will of course depend on S. But given an S, I want to have a construction that gives me a linear sized well-separated pair decomposition. Okay, just to check this concept once more, let's say this is my point set, and the exact distances don't matter that much here. Let's say this is 1, 3, and 9. I want to have a 2 well-separated pair decomposition, so S now should be 2. And my question is, how many pairs do you need? A, 3, B, 4, C, 5, or D, 6? So the number of pairs that we need is 3. So the total number of pairs of distances, so I have 4 points. So the total number of pairs of distances would be 1, 2, 3, 4, 5, 6. So I mean 6 could be a valid answer, but the question is, how many do I need at least? And I can get the following well-separated pair decomposition. So these two, I just have this pair A1, B1. So those are difficult to separate, so I just take the singletons. But now I can group those 2 points. Let's call them A2 and make this one B2. And this is A3. And that is B3. And I've covered this specific set of points with 3 pairs. We want to now come closer to constructing a well-separated pair decomposition. And for the construction, we will use quadtrees. So let me briefly remind you of what a quadtree is. So I have a set of points, and I subdivide my space by always splitting. So by first covering it by a big square, and then always splitting the space into 4 smaller squares. And at the same time, I build this tree structure where the root corresponds to the big square, the children correspond to the 4 smaller squares, and I recursively continue this construction until in every square there's only 1 point left, and that's a quadtree. And just to already get some intuition, why do we talk about quadtrees here? Because to some extent this allows us to eventually build a well-separated pair decomposition, because if I kind of I can take nodes in this tree. So for instance, this square corresponds to a node in this tree. This square corresponds to a node in the tree. And I can try to find squares in the tree that are fairly far apart and put those into the S well-separated pair decomposition. We do that more precisely later. First, we need one more tool, and that is compressed quadtrees. So a compressed quadtree is simply a quadtree where if I have simply a path of degree 1 nodes in the interior of the quadtree, so I mean you can think of this actually. So here in my quadtree, I would first have to split into 4, then split into 4 again, then split into 4 again, then split into 4 again, and only now get different squares for these 2 points here. So the idea is that if I have a path in my quadtree that does not separate any points, I'm compressing that. So I'm removing unnecessary nodes. So here the compressed quadtree looks like that. We don't want to go into detail about compressed quadtrees. The only aspect of them that we want to have, and why I'm mentioning them, is that you can construct for a point set of size n a compressed quadtree in size order n log n. And this will be useful to express how fast we can compute well-separated pair decompositions, because if we use quadtrees, then if you remember, kind of a regular quadtree could have arbitrary size, simply because these 2 points could be very close, and therefore need arbitrary construction time. And that is what we want to avoid. Compressed quadtree allows us to get a running time that only depends on n. Okay, one more aspect of quadtrees that we will need is representatives and then also levels. So we have here for node u in my quadtree the following concepts. First of all, with each u I have a point set pu, which is simply the points within the square of that point. So sigma u is a square corresponding to u, and then I look at the point set within that square. So this is here simply the point set containing p. And now a representative is the following. So for any leaf as a representative, I take simply the point that is in that leaf, if it's a non-empty leaf. Otherwise I take the empty set. I define it as being the empty set. So here there are 3 non-empty leaves. This one here, which is u, and there the representative is simply p, and then I have q and r here. And then for inner nodes, I simply take an arbitrary representative of one of the children. So here, for instance, I can pick between, for this square here, I can pick between q and r. So let's say I take q. For everything here, I can pick between this representative q and this representative of that square here, p. Pick one arbitrarily, gives me p. And those are representatives. Those we are going to use later also. And then we need one more concept, and that is the level of a point, of a node. So the level is the level within the tree if the tree would be uncompressed. Except for a leaf. For leaves, we're going to set the level to infinity. So here in this example, so this is u is a leaf, so the level of that will be simply infinity. The level of the top node is 0. The level of this square here will be, I mean, if you think about it, everything is 0. This one has level 1. These have level 2, so that's level 3. So this is essentially how far down you need to go on the tree. Just for leaves, we set it to infinity. So we now know what a well-separated pair decomposition is. I've covered some preliminaries concerning quadtrees. Now let's jump into actually constructing well-separated pair decompositions using quadtrees. And again, the intuition will be that I'm going to look at nodes, pairs of nodes in the quadtree, and try to find such pairs that are well separated. Let's directly jump into the construction of a well-separated pair decomposition. So here you already see the complete algorithm. It's a recursive algorithm. It's very simple. Let me show it to you line by line. So it works on a quadtree. And so u and v are quadtree nodes, and initially, so it's a recursive algorithm, so we will start at the root, and so initially u and v will both be actually the root, and then we recurse downwards. T is our quadtree, okay, and S is we want to have an S well-separated pair decomposition, so S is a parameter of that. Now we want to have a well-separated pair decomposition of our point set, and in terms of the recursion, if I'm already at node U and V somewhere down, so let's say this is U and this is V, just to have an example, then I want to have a well-separated pair decomposition between points PU and the points PV. So there are some trivial cases to exclude. The first is if one of the two nodes has no representative, meaning it's empty. So if for instance, I'm taking that one, there's nothing to report. So I'm reporting the empty set. Also, if U and V are the same leaf, there's nothing to do because in U and V I just have one point, but the same point, so there's nothing to do. So if they're the same leaf, again, I don't want to report anything. Now, if I have two nodes where the point sets PU and PV are well separated, so let's say I can draw disks here and they're fairly far apart, then I will want to report that well separated pair, and I can represent it simply as a pair of quadtree nodes U, V. Otherwise, let's say I have U and V and the two point sets are not well separated. What do we do? So let's assume U is a node with a larger level, meaning U is a larger square, or it might be same size, also fine. If that's not the case, so that's what we're handling in line 4. If U is further down the tree, meaning that V is larger, we're going to switch the roles. So after line 4, the square of U is at least as large as the square of V. And because they were not well separated, what we do is simply we're now going to split the larger square. So we're going to split the square of U. So we're going to the children of U. And now recursively compute well separated pair decompositions of the children UI with V. And we're going to take their union. And in the description I always said square, but of course it also works in higher dimensions, and you have cubes and split them into smaller cubes and so on. So that's our setting. Let's do this by example. So we start with U and V both being the root, now here shown as a big red square and a big blue square. Now we're going to split and say the blue square, that's my U. Right now U and V are not well separated, I mean they're the same square. So I'm going to split U into 4 smaller squares. So right now still U and V are not well separated because U is a subset of V. So in each of these cases I will need to split further. So let's for instance look at this case here. U was a blue one, V was a red one. Now V is larger, so in particular the level of V is smaller. V has level 0, U has level 1. So I'm going to exchange the roles. So now the blue one will be V and the red one will correspond to U. And we're going to split U, meaning I'm going to split it in 4. So here I'm in this case of the same leaf, so I don't need to report anything. Here I'm in the setting where I'm going to need to ask myself, are PU and PV well separated? For that I need to construct a disk that covers PU and a disk that covers PV. The disks will have the same size, so this could look like that. To construct these disks quickly, what we're going to do is simply we're going to take the disk that goes through the corners of the square of the larger cell, and then we're going to take a same size disk around the other point set. So here, this is the disk that I get if I simply cover the whole square. So I'm ignoring that I could actually make it smaller if I just want to cover the points. And I need to take the same radius for the other point set 2, and I just place it on top of it like this. And now those two disks, obviously, I mean, they're even intersecting. So I cannot place S times R in between. So this is not well separated. At least I didn't identify it as well separated. So now I'm going to split the larger one, or actually I'm going to do it based on level, and because this one has level infinity, I'm going to split the other one. And now, for instance, this is as well separated. Again, you see I'm taking simply the disk around that square. I'm placing a disk of same radius around that point. It is as well separated. So I'm going to report this pair. And I'm going to report it. So this is my pair as such. I'm going to represent it simply as a pair of quadtree nodes. So this node and that node. And then I continue. So for instance, A and D, they are both singletons. So then I get arbitrary small square disks. They are definitely well separated. And then this is my complete list. So some remarks here. The first is, okay, my initial call is simply on the whole point set or the root of the tree. So that's U0. Then this notation is a bit, needs to be taken with care. What does it mean to take the union here? So you should set up the algorithm in such a way that you do not call the same pair of squares twice. That seems like somewhat obvious, but at least as I described it, it would be very natural to get ui and uj, and then at some other point uj and ui. So you should only recurse on one of those two, because otherwise you will find pairs twice. If I have a pair of leaves, okay, if one of them doesn't contain a point, then we're fine anyway. And if they both contain points, because pairs of singletons are always well separated, they are always as well separated, in particular meaning that our recursive algorithm, because it always goes down the tree, eventually we reach leaves. So this algorithm actually always terminates. Obviously, we want to actually prove something about the running time, but at least it terminates. And the output we are going to represent as pairs of quadtree nodes. This will also allow us to get a compact representation. So it could be, for instance, I mean, if I would actually list the AIs and BIs as sets of points, then these lists could get very large. But I'm simply reporting every pair by 2 quadtree nodes, so every pair I can represent with a constant amount of storage. Okay, so this gives us a well-separated pair decomposition. One question about this decomposition: is it minimal for the given S? And the possible answers are yes, because the well-separated pair decomposition for given S is unique, or B, yes, because no matter which S well-separated pair decomposition we take, they'll have the same size, or C, no, not necessarily. And the answer here is C. This might not be optimal. In particular, if you think about the disks that we picked, we did not take any effort in making them smaller to fit the point set. We simply covered the squares. So this is not necessarily optimal, but it also doesn't have to be optimal as long as it's small enough for our purpose. But for that, we have to look at how big does this well-separated pair decomposition actually get. We've seen an algorithm for constructing a well-separated pair decomposition. Let's now look at how large the resulting decomposition is. That is, what is the size of the well-separated pair decomposition that we get, and how fast can we construct it. And this is what I want to show here. Given a point set in d-dimensional Euclidean space and the parameter s, we can compute the S well-separated pair decomposition in time order n log n plus s to the d times n, and s to the d times n here also corresponds to the worst case number of pairs, so the size of the well-separated pair decomposition. If we know how large the well-separated pair decomposition is, the running time is very simple to get. So n log n is simply the time for computing a compressed quadtree, and then from the compressed quadtree, the running time is then actually simply proportional to the size of the decomposition. So and if we can bound that by s to the d times n, we also get this running time. So the size is what we're going to focus on. And I will give a proof sketch of this, also making a simplifying assumption that I can focus on the most important arguments and leave out some technicalities. And the assumption will be, we're going to assume that we have an uncompressed quadtree, and we're going to assume that it has linear size. That makes our life easier. So we want to bound the size of the decomposition. And the size essentially, it corresponds to, or can be bound by, how often do I recursively call the algorithm. And what we're specifically going to count is how often in the algorithm do I go to the recursion. So how often do I go into the else case? So here once more the algorithm. So it's recursive. In these first two cases, that are my terminal calls, because there I simply report something. But my question is, how often do I go into the else case? Because that's where I have my recursive calls. And any well-separated pair has to come from recursive call. So 4 times this number essentially gives us then also bound on the number of pairs. So how often do we go into the else case? That's what we're going to bound. And we're going to use a charging argument. So every time we're going to go into the else case, we're going to make a node responsible for that. And the node that we're going to make responsible for that is this node V. So the node that is not split. Yeah, so node V sits there and tells U to split. Then we make V responsible. We make V pay, and we check how often does V need to pay. So it's a charging argument. We charge every non-terminal call to the square that is not split. And the claim is that any square in this way is charged at most s to the d, so in 2 dimensions s squared times. And that then immediately gives us this bound of s to the d times n, because we have n nodes that can be responsible for splitting. Each of those is responsible at most s to the d times, so overall s to the d times n. Okay, so let's have a look at such a case. So let's say uv is an example of a non-terminal call, where v is the square with the smaller side length, so that will be the one responsible for splitting u. U and v can also have the same side length, but v is the one that is not split. So let's make some observations. So we are in the setting that, okay, uv, for uv we go into the recursive call, so they are not separate. Otherwise, we would have stopped. So what does that mean? It means that we can bound the distance between u and v relative to the size of u and v. And that will be the core of our argument. We're going to see that u cannot be too far away of v relative to the size of those squares. And then there's only a certain number of squares that then can be at that distance, and that will give us our bound. Okay, for this we want to look at the following drawing. So we have v, and let's say this is the radius of the resulting disk, rv. So what we have about rv is essentially, so in 2 dimensions this would be x divided by square root of 2. In general d dimensions this is square root of d divided by 2 times x. So the diameter of this disk is square root of d times x. The radius is this divided by 2. Now, if I also look at Ru, how large can Ru be? So U is split because of v, and we always split the larger square. So what does that mean? It means that actually the difference between u and v in terms of size, in terms of side length, is at most a factor 2. because otherwise we would have earlier split the larger square of the two. Meaning that RU is at most 2 times RV, meaning that it's at most square root of D times X. So we know that these that U and V, or the point sets of U and V, are not well separated, meaning that the distance between them, so this distance here, is at most S times the larger radius, which is bounded by, so this is the larger, a bound on the larger radius, so it's bounded by S times square root of D times X. So that's what I also have in this drawing here already. The distance between the disks is at most S times square root of D times X. Okay, now I want to say something about the distance between the center of U and the center of V, because then I will argue, okay, there can be at most that number of squares with a center inside a certain radius. So what is the distance between the centers of U and V at most? So that is this distance here plus the radius, at most the radius of V, so that's plus this value here. So I take this plus this, and then here to the center I have at most this distance here. So all of these have square root of D times X, square root of D times X, square root of D times X. So I have square root of D times X times 1/2 S and 1. I can bound this, so here we are assuming that S is at least 1. So this is smaller equal S, this is smaller equal S. So a very rough bound here is 3 times square root of D times X. So I know that the distance between the centers, and I'm going to call this now RV, this radius RV, we know that the U to be split by V has to have its center within this radius big RV. Now I just need to count how many squares can I have within that radius. So this radius is, so there's this factor X, which is this factor X, and then I have this 3 times, essentially if you think of D as a constant times X. So if you imagine I have a square of side length X, and now I have a disk of side length, let's say, and I'm saying a constant, so let's say 10 times X. How many squares can I fit into this disk? It's clear that this will be some kind of constant. And the argument that we're using here, I will go into a little bit more detail on the next slide, but this is simply a packing argument, will tell us that there can be at most S to the D times S to the D squares within that disk, or in high dimensions within that ball. And to make this packing argument more precise, so let's assume I have some ball of radius R. I have pairwise disjoint quadtree cells which all have side lengths at most X. Then the question is, how many of these can I fit into this ball B? And the argument, or what I claim here, is that the number of cells or squares of those cells that can fit is proportional to the radius divided by X to the D. So this number here. And the idea to sketch it is, first of all, let's think of this quadtree and this ball. So I have a quadtree, I have my ball placed somewhere, and now I want to bound the number of squares intersected, disjoint squares. Of course, if I make the squares as small as possible, I get as many as possible. So to get an upper bound, it's enough to look at this case where all of the squares have side lengths exactly X. So this is a setting. I have a ball. I have now actually a grid of cells, I want to know how many of those cells are intersected. So if you think of the smaller square here, which has side lengths, the side length is 2 times r, I can ask how many squares does this. So this is this square. Everything that is intersected by the ball is also intersected by the square. So I can ask how many squares does this smaller square intersect. I can look at this dimension by dimension. So how many in this direction, how many squares can I be intersecting? And this will exactly give me per dimension 1 plus 2r divided by x. And then I simply multiply this up by dimension, gives me 2 the d. And that now applied to our setting. So in our setting we were looking at this 3 times square root of d times x sized ball. So if you look at this here, so that's now the radius. I get a times 2, I divide by x, I round this up, I add 1, oh there was an s missing here, I go to the d, then the dominating term here is the s. So the radius was r 3 times was bounded by 3 times square root of d sx. The x goes away, this is just a constant, the s dominates, s to the d is the bound that we get, and that bounds our complexity. Now we will bring all of this back to an initial motivation, namely we're going to construct a spanner using a well-separated pair decomposition. We now have a well-separated pair decomposition. Let's use it to construct a T-spanner. So what was a T-spanner? We wanted to approximate the complete Euclidean graph. So we have a point set. The complete Euclidean graph has an edge between any pair of points, and the weight is the Euclidean distance. And now we want to have an approximation in the sense that we want to have a smaller graph, for instance this red graph here, in such a way that the shortest path in that graph are not much longer than the Euclidean distances. Specifically, for given t, a T-spanner is a graph where the shortest path between any pair of nodes x and y is at most t times the Euclidean distance. And now, given a well-separated pair decomposition, there's a very simple construction to get a spanner, and that is the following. For every well-separated pair, I simply take an edge. More specifically, every well-separated pair corresponds to a pair of quadtree nodes. These quadtree nodes have representatives, and we take an edge between those two representatives. So we take the graph with edges x, y, where x is a representative of a quadtree node u, y is a representative of a quadtree node v, and we do this for any pairs u, well-separated pairs u, v. Just as a reminder, what was the representative? Essentially an arbitrarily chosen point within that square, but it's important that this choice is consistent, meaning the following. So if I have a leaf contains only one point, I take that as a representative. And or if a leaf is empty, I don't have a representative. And for internal nodes, I just take one of the representatives of the children, and that choice is arbitrary. Let's have a look at how this looks like. So here on the left we have a well-separated pair decomposition, on the right we have the resulting graph. So for any pair, let's say this is a representative of that upper set, this is a representative of that lower set, I add that edge. And likewise for this one here, so the representative of that node is this vertex, or that point we already said. Here, let's say that is that's the only point here, so it's also representative. I take an edge, and so on, and this is where I get the graph to the right. And my claim is this is a spanner. it's a t spanner, but obviously the t will depend on my s. So I have s well-separated pair decomposition, parameter s, t spanner, there's a parameter t. So these need to relate. And as I will show next, if you choose s to be this quantity here in terms of t, then if I take an s well-separated pair decomposition, the resulting graph will be a t spanner, and we prove this by induction. We prove this by induction on the distances between pairs of points. So think of this as looking at the pairs of points in increasing distances. So let's say I have such a pair of points. So let's say I have x, y. Now I want to prove that there's a path between x and y in the graph such that the length of that path is at most t times the Euclidean distance between x and y. And I will prove this by explicitly constructing such a path in the following way. So x and y, they will be in some well-separated pair. So what we're going to do is we're going to go, so x is, let's say, in the set pu with representative pu, small pu, y, I have pv. So we have the well-separated pair uv, and we have the representative small pu, small pv. I'm going to analyze the length of the path that I get if I take the path within the graph from x to pu. Okay, then pu, pv, that's simply an edge, and then the graph from pv to y. So what we get is that the graph distance between x and y is bounded by the graph distance between x and pu, then simply the length of that edge, which is the Euclidean distance, plus then the graph distance to get from pv to y. So far so good. Now we have the following. By the choice of s, we in particular also know that s, no matter what t is larger than 2. So why am I saying this? Because it means that within these disks I can apply induction hypothesis, because the distance between x and pu, so if this disk has radius r, the distance between x and pu is at most 2r. Compare that to the distance between the two disks, that will be at least s times r. So if 2 is smaller than s, the distance between the disks is larger than the distance inside the disks, meaning this distances inside the disks are in particular smaller than the distance between x and y, which has to be at least s times r. Applying induction hypothesis gives me here that this is bounded by t times the Euclidean distance between x and pu. Then I have this term here again, and then here I have the Euclidean distance between y and pv. Now I want to express this in terms of r for now. So this here, so they are in the x and pu are in this disk, so this can be bounded by 2r. Likewise, y and pv can be bounded by 2r. So what do I do with pu minus pv? So that's a bit tricky, but can be done. We can use triangle inequality for this. So I want to have an upper bound on the distance between pu and pv. So by triangle inequality, this is bounded by the distance, and this is now Euclidean distance, from pu to x, x to y, y to pv. So I can replace this term here by the Euclidean distance from pu to x, which is 2r, Euclidean distance from x to y, which is simply the Euclidean distance from x to y, plus Euclidean distance from y to pv, that's again 2r. So let's add all of this up. This now gives me, so I have 2r here, that's 4r. I have 2rt here, so that's 4r times t. And then I have the distance between x and y. Okay, I will still need to, so I can first simplify this to 4r times t plus 1, but now I still have this r that I want to get rid of. Now, to do this, I have to set r in relation to x minus y, And what we can use here is that, I mean, x and y are in this well-separated pair. So what I have actually is that the distance between x and y is at least s times r, or if I want to replace r is smaller equal x minus y, or the distance between x and y divided by s. Let's plug this in. Then what we get is the following. I have 4 times distance between x and y divided by s times t plus 1 plus the distance between x and y. Let's now plug in s, our actual s. This will mean that this 4 cancels with this 4. This t plus 1 cancels with this t plus 1. What I have here is remaining for s 1 divided by t minus 1 and 1 divided by s. So this will become t minus 1. Now I have the distance between x and y times t minus 1 plus this distance. So this 1 cancels with this term. So now I have left t times distance between x and minus y. This is exactly what I wanted to show. So we are done. This concludes the induction step and the proof. Good. So we now know we have a t-spanner if we choose s like this. Let's set this into use by picking a specific t, namely the following. Let's ask us what we need to get a t of 1 plus epsilon. So this is a very common setting. So essentially, if you want to do a 1 plus epsilon approximation of the complete graph, or of the distances within the complete graph, we were going to set t to 1 plus epsilon. So how do I need to choose s for this? Do I need to choose it as a constant, specifically 4? Do I need to choose it as of order 1 divided by epsilon, or of order 1 divided by epsilon to the d? So what I'm going to need to do is I'm going to need to set s to something of order 1 divided by epsilon, because then if you look at what happens here, I mean, if I plug in this t up here, so this gives me 1 plus epsilon. I mean, this is 2 plus epsilon for small epsilon, that's essentially 2. But here the t, if I have 1 plus epsilon, essentially this cancels and I just have epsilon here. So I have the epsilon down there, so that will show up here. So the s will be of order 1 divided by epsilon. And what does that mean then if I actually use this for constructing a 1 plus epsilon spanner? Then I will get a spanner of size n divided by epsilon to the d, because the well-separated pair decomposition and the resulting spanner has size s to the d times n. So if s is 1 divided by epsilon, this gives me epsilon 1 divided by epsilon to the d. And the construction time is as we know it. And here once more the derivation, but this is essentially what we already briefly discussed. If I simply plug all of this in, then this is exactly what we get. So this is an O of n divided by epsilon to the d. Good. And in terms of the algorithm, I mean, what we were doing is we construct the quadtree that takes order n log n time. We construct the well-separated pair decomposition that takes, from the quadtree, that takes an additional O of n divided by epsilon to the d time, and then the spanner again O of n to the divided by epsilon to the d time, and that gives us what we wanted to have. Just a few more remarks. So what else can the well-separated pair decomposition be used for? I mean, essentially always when we want to approximate the quadratic number of distances between pairs of points by some small graph. So generally it is useful actually for geometric approximation algorithms. Now, in many settings we can compute, actually using the well-separated pair decomposition is not faster than computing the actual object that we want to compute. So for instance, in 2D, I can use this to compute an approximate Euclidean minimum spanning tree, but I can also simply compute a Euclidean minimum spanning tree in order n log n time. But in higher dimensions, this is very useful. And there are very interesting kind of connections between well-separated pair decompositions on the one hand, de Launay triangulations on the other, and that kind of gives me some kind of equivalence between lots of different data structures, which is to some extent somewhat surprising, given that, I mean, a well-separated pair decomposition I compute from a quadtree. A quadtree looks very different from a de Launay triangulation, but still computationally they're actually very closely related. And one last fun fact is the following. So concerning the greedy spanner, so the greedy spanner, so in a previous iteration of the course projects were about spanners, and actually from that time there are many new results about the greedy spanners. So in particular, a construction that only uses linear space and near quadratic time. And that's all for today.